So our assignment for this Dropbox, lesson 3, kind of goes on a little bit of a tangent from the Lewis structures that we just did. So Lewis structures, we said, are kind of grid 11, but we really need to know a lot about them in order to get through the rest of this unit, which includes hybridization. Hybridization can be super scary. If you want to know more, by all means, I can send you in some other directions. We're going to very much so simplify it and just look at the idea of hybridization. So where hybridization comes from is kind of, we're working backwards. So we looked at a molecule of methane, methane being the very first Lewis structure we did together with a central carbon atom bonded to 4 different hydrogen atoms. And we said it's a simple molecule. We quickly put all 8 electrons onto our Lewis structure and we moved on. When we get to Vesper in our next lesson, we'll see that a molecule of methane is a tetrahedral shape, which means it has 4 different bonds, all at this equal angle of 109.5 degrees. Cool. However, if we were to look at quantum mechanics now and electron configuration and hone in on this carbon, we know that carbon's electron configuration is 1s2, 2s2, 2p2. In order to make a bond, and why we always said like carbon has ownership of 1 electron of each bond, it needs to have half-filled orbitals in order to take its 1 electron and bond it to the 1 electron from hydrogen. So we need to somehow open up 4 bonds in order to actually allow, open up 4 orbitals, my bad, in order to actually allow bonding to happen. So that's the first thing we need to do. Before hybridization can happen, we need to do electron promotion, is what it's called. We need to take one of these 2s electrons and promote it to become a 2p. So it's easier to see here. That's when we've taken one of these 2s electrons and pretty much brought it over to this third orientation of 2p. We now have 4 different spots where we can bond in order to make this molecule, which seems like a done deal like we did last time. The weird thing is we've already seen different pictures of s orbitals and p orbitals, and we know they look much different. But we know that a methane molecule has these perfectly 109.5 degree angles. So they all have to be the exact same. This 2s would obviously be a bit different from these 2p's. And that's where hybridization comes from. We're going to take this s orbital and these 3 different p orbitals and hybridize them to become the exact same type of orbital so that they can make the exact same bond. And so since we've taken one s and 3 different p's, we've made an sp3 orbital. And since we've taken 1s and 3 p's, so 4 orbitals total, we've made 4 hybrid orbitals by hybridizing 4 different orbitals together. And so if we have sp3s, we've hybridized 4 different orbitals, we know we're going to make 4 bonds. Cool. This can show us, without going through that whole process, about the different types of hybridization that we can do. So if we need 4 bonds, we need to hybridize 4 orbitals. If we need to make only 3 bonds, and these shapes we'll learn in our next lesson, we only need to hybridize 3 orbitals. So we're always going to start with an s and then just how many p's we actually need to use to make that orbital. So 2 p orbitals plus 1 s orbital can make us 3 bonds. If we only need to make 2 bonds, we only need to hybridize 2 orbitals. We also saw when we were doing Lewis structures that we have things that are expanded octets. We're going to make more than 4 bonds. So if that happens, and we need to make 5 or 6 bonds, we have to start getting D's involved. So sp3d, sp3 was 4 bonds. If we add a D, we can now make 5 bonds. And if we need 6 bonds, we need to bring a second d orbital in. And now we're hybridizing 6 different orbitals. It looks super funky, but at least we'd be able to make consistent angles, so every bond looks the same. So that is hybridization in a nutshell. Then we get to our assignment to just see what kind of hybrid orbitals are needed for certain types of molecules.